All right. Good morning, everyone. Welcome back to Math 154, our 10th week, first lecture together. Not too many weeks left. It's kind of crazy how fast time flies, but per usual, let's go ahead and talk about our whiteboard for a few minutes before we begin our lecture. So my math lab homeworks 4.2 and 4.3, you've seen those dates before of 10/28 and 11/2. 4.4, we said last class, week 9, lecture 2, that we had finished that section in terms of the material in the homework, in terms of the material that would be on the midterm. However, I am still going to do one, I'm going to call it a fun problem. And fun's not really the right word for it in terms of the content, but just a challenge question, something to expand our minds a little. And again, this is something that wouldn't be on any homework, on any reviews or any tests or anything like that. And then after we finish that problem, take us about 15-20 minutes, we will go into 5.1 where we start our discussions of lines, which will be something that's very, very important moving forward. So the biggest important reminder is that we said our midterm is going to take place on November 1st and November 2nd. So you have 2 full days to do this. Now you might be saying, Mr. Beckner, November 2nd is election day and TCC is closed that day. Sure, there are no classes on November 2nd, but that doesn't mean I can't have a take-home assignment still open and valid that day, especially since technically I only have to give you 1 day for a midterm. So if you don't have the ability to take it on the 2nd, that means you need to take it on the 1st, that Monday. So that shouldn't be too big of a deal. And hopefully you can get your voting taken care of in an hour or two, and then you'll be able to focus on your midterm if you do have to take it on the 2nd. But again, TCC will be closed. There should be no classes on that day. If you have a teacher that's holding class that day, let them know that that's not supposed to happen. This is actually new for TCC. I want to say we've only gotten election day off the past 2, maybe 3 years, including this year. So some professors might not be used to that particular thing. So the midterm, 20 questions. I know I had said it was between 20 and 25. We're going with 20. You'll have 2 full hours to take it. If you have any kind of accommodations for anything having to do with that, shoot me an email as a reminder, and I will make sure that you are accommodated. Remember, the midterm is going to be located in my math lab. When you go under your assignments, it will be the very top assignment, but only during those 2 days. I can't make it visible any sooner, or else you would have access to it, and that's not going to happen. The same is true of where you'll submit your work in Canvas. There will be a spot that you should be able to easily find where you will submit your work. It'll be where the midterm review is and all that stuff, the formula sheet. So only the 2 days that the midterm is available will you find the work submission. Please make sure you submit the actual work there. Don't submit an Excel file. You will not be able to re-upload anything. It's a 1 submission only. Remember that you do have to submit your work within 15 minutes. You have to make sure your name is on every page. You have to make sure that your problems are numbered. If your work is poorly organized, I don't have to give you any partial credit. If you don't submit your work, I reserve the right to give you a 0, and I don't want to have to do that. So again, you're going to take the midterm at your quote leisure at any point during the 1st or 2nd of November. It will be closed at 11:59 p.m. November 2nd. And you have to do this in 1 sitting. You can't open the midterm, work on 5 questions, and then close it and open it later. You have to do this in 1 sitting. You have the review that's in Canvas. We've talked about that previously. It's about 55 to 60 questions. It is very comprehensive of what you'll see on the midterm, but it's not going to be just a one-to-one question, obviously. So that will give you a clue on what to focus on studying. And then you'll see a very, very short formula sheet provided in Canvas, which again is just a couple of conversions, something like how many centimeters are to an inch, or how many gallons or how many fluid ounces. I'm not saying that's what's on it. I'm just giving you an example. Remember that for conversions, you have to know everything having to do with time, like 60 seconds is a minute, 24 hours is a day, 365 days is a year, etc. All the different formulas we've talked about this semester, like how to go from an annual periodic rate to something smaller, like a monthly rate or a daily rate, whatever you might need for a problem. That's not going to be on the formula sheet. How do we calculate percent change and total change? That's not going to be on a formula sheet. These are formulas that you were supposed to have memorized that we've given you. And all of those, quote, formulas were generally just 1, maybe 2 steps. So I don't even call most of those formulas, I call them concepts. So those are the expectations. I will not give any makeup midterms if you do not submit this in time, unless you have some proper medical documentation or court documentation that I would have to submit to my bosses and all that good stuff. We do have paper trails nowadays. It is 2021. So make sure that if you know in advance you can't take that midterm those 2 days, like you're going to be out of the country or something, or you're going to be in the middle of the woods with no internet for a family trip that's been planned forever, you need to arrange to take that sooner than later. I will not give makeups after November 2nd. All right, so let's go ahead and, like we said, do that quote fun, and I'm saying fun lightly, example that's just a conceptual problem from 4.4, and then we will go into 5.1, and I'm just going to give a quick little summary about 4.4 before that as well.
All right. So, and last time we did all of these problems, we talked about this growth factor, this growth decay rate, this new equals original times the 1 plus or minus X%, where again, this right here was your growth factor. This thing right here, or decay factor. So with the slash does not mean division, I'm just saying or decay factor. It depends on whether we're acquiring more things or losing things. And both types of problems are seen in the real world. When we talk about radioactive decay, we're using, well, spoilers, decay factors. We talk about isotopes being lost from something, that's a decay factor. When we talk about gaining money by acquiring interest as a percent over a day, a week, a month, a year, whatever, that's generally using a growth factor. This idea of a growth factor, this idea of new equals old times growth factor, again, new equals old times growth or decay factor. This is not going to go away. This is going to be seen for the rest of the semester. This is going to be a common theme. We're going to create an entirely new equation out of this in chapter 6, known as the exponential equation. And yeah, so this is not going away. How do you know whether it's plus or minus? Add if growth, subtract if decay. I think I said that wrong. Add if growth, subtract if decay. No, I did say it right. And then I also pointed out that you don't have to be given the old and the growth rate to find the growth factor and then multiply them to get the new. I could give you the new and the growth rate or factor, and you could find the old by just doing some algebra, and we saw that in our example. So again, I don't want to completely go over all those again. If I've lost you, go watch the class from a week ago, which again, thank you for your patience with me dealing with that situation. And this was probably my favorite thing that we did there. And I thought it was really funny with the timing. Someone in my life was just literally talking to me about that the same day. They were talking about how a lot of people don't understand that if you have a 30% growth and then a 30% loss, that you're not at the same point, that you're actually behind. So you need higher growth percents to make up for whatever loss percent. So if you lose 25%, you need to gain like 33% back just to be even. It's kind of like that. And the bigger the number on as a loss, the even bigger the number needs to be as a gain. All right. We talked about our total change with percentage points in 4.4. And we did that problem with Bob. We talked about the very important language, because otherwise it's confusing, and we talked about why it's confusing. How we say percentage points when we're talking about a total change of a percent. So like, oh, we got a pay raise of this percent 1 year and then a pay raise of this percent 1 year, because we're talking about a change of a percent, not a change in apples or a change in money. The total change would be a percent, and then the percent change would also be a percent, and that's confusing. So that's why somebody just one day decided to use the phrase percentage points to represent the total change of a percent. Now, this idea is not going to stick with us all semester. It will be in the midterm. You might see one on the final, but we're not really going to play around with this too much more, just as an FYI. But again, you will see this in the real world if you ever watch the news. You'll be talking about percents of percents. And again, just to avoid the confusion, there's specific language. All right, so this sobering problem, the thing I said that's just going to get our brain waves firing, our cerebral cortex is firing, however you want to say that. Drunk drivers are responsible for 33% of motor vehicle deaths. So this was a statistic I pulled up maybe a year and a half ago. So that means if drunk drivers are responsible for 33%, again, roughly, not again, but roughly 1/3 of motor vehicle deaths, that would mean that sober drivers are the cause of 2/3, roughly, or 67% of all motor vehicle deaths. So if drunk drivers are causing 1/3 and sober drivers are causing twice as many, 2/3, why is it that we don't have more news and more worry about our sober drivers? Why do we have so much more focus on, and I don't want to say just drunk driving, let's open this up to intoxicated driving. So not just being intoxicated from alcohol, but any other substances, which we don't need to list. So why is it we focus so much more energy on the intoxicated drivers versus the sober drivers? Now you might say, well, Mr. Beckner, we do put some energy into some of the sober drivers causing issues like texting and driving. That's a very, very common one, or just being on your phone at all in driving. Even with hands-free, there's a lot of theories that say hands-free doesn't really make you much safer. You know, we could throw some percents out there, but they'd be off the top of my head. I didn't come prepared for that today because this is not the whole point. So what are the sober drivers that could be causing issues? Well, the people eating and driving, or having a sip of a beverage that's not alcoholic and driving. Of course, that other scenario would be part of the first problem. So we have just distracted, just talking to people in the car. If you got a car of 4 or 5 people and you're laughing and having a good old time and music's blaring, you might be paying attention to the road less. So just distracted driving. And then you could say, well, there's also a small portion of people that maybe have an aneurysm or a heart attack or some medical condition while they're driving to cause the accident that could cause a death. So again, the sober, we've got all of those different scenarios, whereas the intoxicated drivers, it's just intoxication through various substances. So again, the point of this question after all that rambling is, why are we not putting more energy? Why do we have so much MADD and sober checkpoints and all this other stuff? There's a lot more energy focused on these people that are causing half as many deaths. The point of this is, it's all about scale. It's all about size of a population doing something. So let's say this red circle, actually we'll do black. Let's say this black, quote, circle, oval, represents all drivers. So this is all drivers on the road. Now I want us to split up this population. Out of the 100% of drivers, I want us to try and think about, how many people on the road at any average time would be sober versus intoxicated. Now, yes, it's true that at 2 a.m., this ratio would change. So again, we're thinking on average. We're thinking, 4 p.m., 9 a.m., when most people are on the road. We're not necessarily just exclusively focusing on 2 a.m., 4 a.m. of Independence Day or New Year's Eve or anything like that. So if you just go out at 2 p.m. on a Thursday, most people aren't going to be intoxicated on the road. Yes, there will be some, but most people would not. Now, when I say most, we got to kind of put a number to that. And maybe you're thinking 80%, maybe you're thinking 90%. But even when you lump in all of those people at 2 a.m. and 3 a.m., it turns out to be about 95%. And again, this is a rough statistic, so don't just use this as the gospel. About 95% of the people on the road on average across all 24 hours of the day are what we call sober drivers. And then this other, we'll do it in red, this roughly 5% are the intoxicated drivers. So again, an average on any moment on the road, averaging across all 24-hour blocks. This is roughly saying for every 20 drivers out there, 1 is intoxicated and 19 are sober. Now again, at 4 p.m., the statistic's a little different. At 9 a.m., the statistic's a little different. At 2 a.m., the statistic's a little different. We're just averaging. So the sober drivers here are causing 2/3 of deaths, again, 67%. But the intoxicated drivers, this teeny little chunk, is causing 1/3 of deaths. And when you look at it this way, it starts to make a little more sense because we're talking about scale to the population size. So this teeny little chunk is causing 1 out of every 3 deaths on the road, whereas it takes this massive chunk just to cause the other 2 out of 3. If we needed to focus a lot more energy on the sober people, it would be a ratio of maybe like 50% are sober and 50% are intoxicated. If that was the ratio of sober to intoxicated people, then first, yes, we would need to put more energy into the sober drivers. And second, we need to start worrying about why half the drivers are intoxicated. That's a big problem. And, you know, post-election day, I could make some jokes. Just imagine I made some jokes. But we're talking about life and death, so I don't want to take it too far on the internet. I'm trying to keep it light though. But again, the point of this problem is just blatant statistics. Oh, drunk drivers are causing, or intoxicated drivers are causing 1/3 of deaths. Sober drivers are causing 2/3. We need to focus more energy on the sober drivers. They're running rampant. We've got to fix this. This is how statistics get misused in the media. Because yeah, again, while that's true, 1 out of 3 versus 2 out of 3, this is a tiny, tiny, tiny population in comparison to the size of the population causing just twice as many. And again, I'm saying, quote, just twice as many. It takes one person to cause 1 death, maybe, and then it takes 19 other people to cause 2 deaths, which you could argue that means 17 of those other people aren't even doing anything. All right, so population size, thinking about the dynamics inside of that population, especially if we're talking about one group doing one thing and another group doing another thing. And this is applicable in so many different ways. We can talk about, you know what, I don't want to get into those details because we are behind. But again, there are lots more applications of that concept. Just use your imagination. The one thing I do want to point out that is in the material of this section that I'm not going to test on, however, it is an extremely cool concept that honestly goes along with what we were just discussing, are two-way tables, which are used for data involving 2 specific categories, such as gender or political affiliation, or maybe a drug test, whether you get the actual drug or you get a placebo. You can use this in different testing, like you know, a certain coronavirus, whether you get a positive or negative result and whether it's true or false. And then you can start getting into some light statistics, whereas what's the chance that if you get a positive result that you're actually positive, or if you get a negative result that you're actually negative? Because this is another scenario where when you look at statistics, you look at the numbers and you go, oh, well, that's very obvious. If 95%, yeah, you're good. But in fact, when you start doing the actual probabilities, which again, I try and keep the statistics out of this course, which is why we're not doing it. It turns out that even some of these, like, oh, you're 9 out of 10 fine, even if you get a positive result or whatever, things like that. It turns out that things can go sideways a lot quicker than you would imagine in terms of just the math behind it. It can be misleading is all. So two-way tables, something to check out on your own time if you'd like. I would really love to make to have time on my hands to make a collection of videos for all the things we don't talk about that I could just have linked on YouTube and say, hey, check this out if you're interested. But I'm not ready for that yet. All right, so that is chapter 4. So what we can do now is dive into chapter 5. And I definitely need some spacing here. Let's go. I'll put all this down. There we go. Sorry, I was looking at something. So chapter 5, which will not be on the midterm. Once again, the midterm only covers chapters 1 through 4. Everything from the first day we talked to where I just finished right then and there. That is the midterm, the first 4 chapters. I know it doesn't feel like a midterm because we're into November at this point. It's more like a 3/4 term. Admittedly, this midterm should have been a week ago, but we missed some classes due to random things and rambling and stuff, so let's not ramble more. Chapter 5, proportionality. Well, hold on, Mr. Beckner. Proportionality? Come on. We've been talking about this since chapter 2. We did it in chapter 2. We did it in chapter 3. We did it in chapter 4. So how can you say this is new material? Well, we've been able to make it new material the whole time before this, so I don't think I'm going to have a hard time making new material out of proportionality again. Now what we're going to do is we're going to start studying it in a graphical manner and not always as a proportion. It will, a lot of the times our graphs will be in the same kind of universe as proportionality, but not on the same planet. Sorry, I was trying to think of a way to word that. But when we talk about the idea of proportionality, whether it's actually proportional or just kind of proportional, and we'll get to what makes it kind of proportional later, the graph of something that's proportional or proportional-ish looks like a line. This is a line. Now, some people have the misconception that this is also a line because it just keeps moving and we don't lift our pen. This is not a line. This is what we call a curve. Some people will call that thing on the left a straight line, which is redundant. Calling a straight line is redundant because a line by definition is straight. It's like saying a crooked politician. It's redundant. I'm sorry. I know that's a horrible joke. Oh, the cheese is real. So lines are straight. When you go outside of our course, when you go to the real world and someone says that this thing is a line, you can verbally slap them on the wrist, so to say, and it's like, no, 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 lines are straight. Now, again, a lot of times when we're talking math in the real world, no one cares about bad lingo and things like that. I was actually just helping someone study for a shipyard exam. We were talking about exponentials and logarithms, and they used the word opposite when they should have used the word inverse. I was like, well, you know, it's kind of slang to say opposite, but the better word is inverse. And then it actually helped them out. So again, real world, somebody might call this a line. Don't be a jerk about it and just go, well, you know, if you want to be technical, it's really a curve, but I don't care if you call it a line because you're not going to affect my life. This is a line. Lines are straight. Now we're going to use something known as the rectangular coordinate system, which has another name, just like a lot of things in the world. It's also known as the Cartesian coordinate system. And this is something that you were supposed to have done in your prereq courses, which I've said about a lot of things, but we don't assume too much. So we give you a quick introduction, but say, all right, if you don't remember how to do this, you need to get to it quick. So a rectangular coordinate system or a Cartesian coordinate system, whichever name you give it, and those are interchangeable, we draw two lines and we label them X and Y. The horizontal has to be labeled X, the vertical has to be labeled Y. And those are what we call our axes. So those are our, specifically the x-axis and the y-axis. Where they cross, they meet right here. That's where they cross. We call that the origin. And then what we say is, any location in this flat plane, so if you have a piece of paper, any location on that piece of paper, if you're looking at a wall, any location on that wall, or if you believe that the Earth is flat, which is wrong, but if you did, then any location on the Earth could be described with a coordinate pair. Now, because it's just a two-dimensional mapping onto a sphere, you can still do the same thing. It's just not technically a rectangular coordinate system, but we're not going to get into all that. So what we're saying is that this point can be described with a pair of numbers. This point can be described with a pair of numbers. This point can be described with a pair of numbers. And we always go the left or right number first, and then the up or down number second. So if I go right, let's say A units, maybe this is 5 or 7 or 3 or whatever, and then I go up B units, this point right here, we would have in parentheses, and it goes A comma B. We go right and then up. That's what I'm trying to describe here. We go right A units and then up B units. Now we could have gone left and down or left and up or right and down. Those are all options as well. It just means that you might have a negative value on the x value or the y value. The first one is always the x value. The second one is always the y value. The A was on the x-axis, which makes it the x number. The B was on the y-axis, which makes it the y value. If I swap these two things, it would be wrong. You have to go left or right and then up or down. So something a little more specifically, if I went right 3 and up 1, this point right here would be 3, 1, not 1, 3. If we went left 3 and then up 1, it would be negative 3, 1. If we went, let's say left 3 and down 1, 2, 3, 4, 5, this would be negative 3, negative 5. Well, Mr. Beckner, what about if you don't move at all? What if you're on the origin, like you said earlier? Well, that point is 0, 0. So what I was saying earlier is right here now. How do you plot coordinate pairs? That's what we call the x, y, or the a, b, or the negative 3, 1. It's a coordinate pair. A pair because it's two numbers. So a coordinate is how we can describe a location. If we're trying to describe something in 3 dimensions, it would be a coordinate triple because you'd need 3 numbers. You need to go how far left to go, how far up to go, and how far in or out to go. So the first value tells you how far left or right. The second value tells you how far up or down. Left is negative, right is positive. Down is negative, up is positive. If you're getting these wrong, practice it. If you're still getting it wrong, practice it more. If you're still getting it wrong, you know what I'm going to say, practice it more. Just because there's only 3 or 4 or 5 homework problems on this does not mean you only need to do 3 or 4 or 5. Some of you are probably good after 1 or 2. Some of you may need 10 or 12. Hit the similar exercise button. Go to other resources, whatever you have to do. Because we will be plotting some lines in this course. We're not going to do a lot of curve plotting by hand, but we will definitely plot some lines by hand. And the types of curves that we plot will not look anything like the one you're seeing over there. They usually look more like this, and we usually let Excel plot those for us. We don't need to get into all the fancy stuff about plotting exponentials. All right. Do I want to go ahead and talk about this? Yeah, we will. Look for patterns with larger tables of values. This is going to be relative to the guided exercise we're going to do in just a little bit. When things are on a line, what we're going to really get into is how, let's say you have this point right here, and you know it's what we call rise and run. You can run to the right, and then you can rise to find another point, and then you can run to the right and rise to find another point. And you would be told, or you would figure out how far right and how far up you're going, or how far right and how far down you're going. So you get right and up. And these distances are always the same. And the point is, this pattern continues forever and ever and ever. So instead of just plugging in numbers, processing them algebraically and simplifying to get a number for your output, you could just keep doing this over and over and over and over and over. If you go right 1 and up 5, the next time you'll go right 1 and up 5, and then the next time you'll go right 1 and up 5. So if we're looking at a table of values, to find that pattern, we can look at the table of values. Pay attention to how much the first value is increasing, and then how much the second value increases or decreases. If this remains consistent, you may be able to make quicker conclusions about future data. As I was just saying, you could prevent yourself from having to plug in an x value, do the math, and find the y value. You might be able to say, oh, well, the next one go up 50, 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 the next one go up 50. But you have to be consistent in one versus the other. If your x value goes up 10 and then it goes up 50 and then it goes up 70, that's not consistent. You would need the x value to keep going up 10 every single time to be able to draw that conclusion about the y value consistently going up the same every time. And it doesn't have to be 10, it could be 5, it could be 1, it could be a million, it could be whatever number. It just needs to be a pattern. Now, ultimately, I want to go ahead and point this out. You only need 2 points to form a line. All extras are just for checking. If you don't believe me, here are 3 points of a line that I just found. Look, there they are. And if I connect them, if I'm a perfect artist, then these would all go through like so. This one is a little off. Just gonna make them a little bigger, a little more exaggerated. So check this out. If I erase one of these points, so I had 3 to form that line. If I pretend like I never had the middle one, does that change the image of the line? Nope, it doesn't. If I deleted this first point, okay, well, I didn't mean to delete the line too. Sometimes the eraser is a little wacky. There we go. Boom, it's still the exact same line. If I were to erase this third point instead, it's still the exact same line. If I had 4 or 5 or 20 points, this line is still going to look the exact same every single time I add another point because the pattern is consistent. Ignore this difference in sizes of them. I'm just trying to show you a whole bunch of different points. No matter how many of those points I have or keep adding up there, it's not going to change the picture. That is the point of graphing a line, because each one of these points just represents one solution. So I've got 1, 2, 3, 4, 5, 6, 7, 8, 9 solutions shown here. But what you can visually see in between those is the trillions of solutions. I'm not dashing this, I'm just putting trillions of little dots that are everywhere in between the 1 or 2 or 3 that you found. This is very much saying a picture is worth a trillion, a billion, 1,000, whatever unit words you like. And it shows how the pattern keeps going in either direction. So maybe you got a number for x equals 1 and 3, but your boss says, what happens when x equals a billion? Well, you can use this picture to project that. All right. So let's get into the guided activity, and I did not open my MATLAB. Give me a minute. Oh, sweet, it saved my sign-in. Usually it kicks me out by now. Text, chapter 5, guided worksheets, boom. Humana, and this is going to be another one of those cases where I am going to use the slightly crummier handwriting on this thing because it would just be really difficult to do otherwise. So things will get erased as we go. So chapter 5 is all about linear functions, and 5.1 is called proportionality. I think I didn't say this, but chapter 5 is all about what we call lines. That's why the first thing we started talking about was lines. So we're introducing how proportions or how lines can sometimes be proportions and sometimes they're not. And again, when they're not proportions, they're still proportional-ish. They still change kind of like a proportion. It's just more like that temperature issue where 0 and 1 isn't necessarily 0 and the other. We talked about how all unit conversions are proportional with the exception of temperature because 0 degrees Celsius is not 0 degrees Fahrenheit. That statement right there very heavily ties into how lines are sometimes functions, are sometimes proportions and are sometimes not proportions. I saw this word function there, and that's what made me say it out loud. I didn't mean to say it. So ratios, proportionality, lines, all heavily tied together. And we're going to start studying this by talking about cell phone plans. And, you know, it's kind of an archaic cell phone plan, and these still do exist out there sometimes, but most of us have unlimited minutes at this point in our life. Most of us have unlimited text messages at this point, probably. All right, so this table is going to show the cost of monthly track phone plans as proportional to the number of minutes talked at rates of 5 cents and 7 cents per minute. So they're proportional, which means if you double the number of minutes you talk, then the cost you're going to pay is going to double as well. So what we're saying here is one plan, if you talk 1 minute, it costs you 5 cents. If you talk 2 minutes, it costs you 10 cents. If you talk 3 minutes, it costs you 15 cents, 4 minutes, 20 cents, etc. Versus another plan that 1 minute's going to cost you 7 cents. Second minute's going to bring you up to 14 cents. Talking 3 minutes is going to cost you 21 cents. Talking 4 minutes is going to cost you 28 cents, etc., etc., etc. Now, the first thing you're going to think is, well, why would you want the 7 cent per minute plan? Give me the 5 cent per minute plan. That's just silly to pay 2 cents more per minute. Well, we'll get into why you might take that one later. Spoilers, hidden fees. So from table 5.2, we created a graph, an XY scatter plot, coordinate pairs, rectangular coordinate system, Cartesian coordinate system, all that stuff's the same thing, which gives us a visual display of the relationship between the inputs and outputs, inputs being the number of minutes, outputs being the cents. Noting that the points for all functions all fall in the line starting at the origin. Now, this right here, starting at the origin, spoilers for later, but this is what makes them proportional. Because 0 and 1 is 0 in the other. 0 minutes means you pay 0 cents. So when your lines start at the origin, they're proportions. When they don't, they're not. That's the end-all be-all of whether lines are proportions or not. But even when they're not proportions, they're still proportion-ish. Which again, that whole rise and run thing is where that's going to come into play. And then we see a lot of things that I've already said out loud, so I'm going to go ahead and scroll down after I clear that. So here's our graph. So in blue, so the cool color blue is the nicer plan for now because we're paying less per minute. So 1 minute costs you 5 cents. So let's focus on the table for now. So 1 minute costs you 5 cents. 2 minutes costs you 10 cents. 3 minutes costs you 15 cents. So this right here, just looking at these two things, is the 5 cent plan. Looking at these two things is the 7 cent plan, so number of minutes and then the cost. I'm not a huge fan of how they set this up. I wish they would have done the more traditional way of just doing 2 tables of values. So for minutes and then cost, which is the 5 cent plan, we would just go 0, 0, 1 minute costs you 5 cents, 2 minutes, 10 cents, 3 minutes, 15 cents. And then you could have the other one, which I'm not changing the colors, the cost for the 7 cent plan. 0 costs 0, 1 costs 7, 2 costs 14, 3 costs 21. You get the idea. These are 2 independent tables of values, but it's still fine to do it this way. It's just when you have it this way, it looks more like an Excel issue where this is your input and these are your outputs based on the different costs. So 0, 0 was this point. 1, 5 is this point. 2, 10 is this point. 3, 15, right 3 up 15 is this point, and then you just connect them. Now, you saw me draw a line earlier that looked like this, where I put arrows on both ends. In this course, in this quantitative reasoning course, however, a lot of the times going into the negative region won't make sense. We can't talk a number of minutes, so it doesn't make sense to extend the line in this direction. So we don't. We can't talk negative minutes, so we don't draw that up. Now, what we could do is we could keep extending the line this way because this pattern will continue. It will continue forever and ever and ever, as long as it's not a complex model. And the same for the other one. So when we talk 0 minutes, we pay 0 cents, 1 minute, 7 cents, 2 minutes, 14 cents. Here's the 0, 0 still there. 1, 7, 2, 14. Now 14 isn't up here, so it's a little bit lower than the 15. And then 3, 21, that 21's a little higher, and the 7 was there as well. And that's how you get these points. You connect them. And the way I would prefer things are done outside of this little page right here is you extend it because the pattern continues indefinitely. So that just looks a little better now with the arrows on the ends. Now, this right here, this right 1 and up 5, this is what I was talking about before with the consistent patterns. Every time we add 1 minute, this is going up 5 cents. Every time we add 1 minute, this is going up 5 cents. Every time we add 1 minute, this is going up 5 cents. Or for this column over here, every time we go up 1 minute, this goes up 7 cents, up 7 cents, up 7 cents. So if I gave you an equation for this, or if I asked you for an equation for this, you don't really need it to continue this pattern. You could just say, all right, well, if we go to 4 minutes, which is one more, we'd expect the 5-cent plan to go up 5 cents, which would be 20, and we'd expect the 7 cents per plan to go up 7 cents, which is 28. If we talked 5 minutes, which is another up 1, we'd expect this to go to 25, which is up 5, and we'd expect this to go up 7, which is 35. So this is a great way of finding patterns to extend your tables, which is what I had on those notes earlier. So every time we go right 1, that's the 1 minute increase, this goes up 5 cents. Or for the other plan, every time you go, let me put it up here, every time you go right, that's adding 1 minute. This one goes up instead 7 cents. And see, that's consistent. Spoilers, this relates to what we call slope, if I haven't already said that. Now, this problem was proportional, both of those, because 0 minutes was a 0 cost, so that makes them proportional. If 0 minutes cost you more than 0 cents or dollars, it would not be proportional, but again, it still just relates to it. And the relation is this, as you see an increase in one way, the increase in the other way or decrease in the other way is consistent. So proportional means if you double one, you double the other, which means if you go up a certain amount in one, you go up a certain amount in another. That's the same idea as this, going up a certain amount, then go up a certain amount in the other. It's just, you just can't say if one doubles, the other doubles. That's the only difference there. All right. So let's take this problem that we just did. We're going to go higher on the minutes. We're not just going to talk a couple minutes. We're going to talk hundreds of minutes. And now what we're going to do is we're just going to talk about the 5-cent plan, and we're going to input a hidden fee, so to speak. So now we've got a $20 fixed cost as part of this problem, so it's a lot more realistic to a true cell phone plan. Most plans aren't just pay by the minute. They're, all right, if you don't talk at all, you're still going to pay 30 or 40 bucks. If you talk forever, you're probably going to pay 35 or 40 bucks maybe, I guess. But we're going to do it based on these numbers. So cost is proportional to minutes you speak at a rate of 5 cents per minute. Again, that is what we saw earlier. This is nothing new. Cost is proportional, which means if you double one, you double the other. But now we're also going to assume that on top of that, there's an additional fixed cost of $20 each month. So that's our taxes, our fees, etc. So what we have here is, I'm going to go ahead and get the graph up here. If you ignore this, that's what we were just doing before, but now in hundreds of minutes. So our cost is now in dollars. So 100 minutes would be 500 cents, which is $5. 200 minutes, $10. 300 minutes, $15. 400 minutes, $20. We're only talking about the 5-cent plan, not the 7-cent plan. But again, this is not the true cost. Your true cost is over here. That was weird. Undo, please. Thank you. This is the true cost with everything accounted for. So you had what we call the variable cost, which was your minutes, but then you have your fixed cost, which doesn't depend on how many minutes you talk. So that's this just extra $20 you slap on the bill no matter what. So if you pay 0, that's what the dash means, $0 in your minutes, you still pay $20 for the fee. If you talk for 100 minutes, you pay $5 for your minutes, but you still pay that extra $20 for the fee, bringing your total cost up to $25. If you talk 200 minutes, your minutes cost is 10 bucks, add in your fixed fees, and you got a $30 cost, et cetera, et cetera, et cetera. Now, it's still pretty easy just to, all right, well, this went up 5, this went up 5, this went up 5, every time this went up 100, every time this went up 100, every time this went up 100. The same is actually true over here. This still just goes up 5, this still goes up 5, this still goes up 5. Now, it doesn't go up 5 from these numbers, it takes these numbers and adds 20. So just to go from here to here, you're adding 22. Again, that's your fixed cost. A fixed cost is just added at the end. So we have two types of cost here, which will be laid out on the notes in a few minutes. a variable cost and a fixed cost. And the words variable and fixed mean they change or they don't change. Just kind of like when we fix Excel references, we say that it's not that they were broken and we unbroke them, it's they're rigid, they don't change. So that's what we mean by fixed, it doesn't change. This is kind of like your rent. Your rent doesn't change every month. Your electric bill might change, your water bill might change, but the actual rent does not change until the next year, maybe. But then you can just make a new model after that. This is a very important concept. This is going to be seen all chapter long, and the concept will go into the real world with you. A lot of things in the real world are just based on a sum of a fixed cost and a variable cost. The word variable means change. Fixed means it doesn't change. All right, so what's all this stuff down here? And again, you could say, all right, 600 minutes without the fee would cost you 30 bucks, fee accounted for 50, and you could keep going. And they only plot the first 4 points. They don't do the 400 and the 500 just because they were going to run out of room, I guess. So the red one is just the 5-cent plan without the fixed costs accounted for. So because this one starts at the origin, this one right here is proportional. I really don't want that color though, since it's red. So this one is proportional because it starts at the origin. This one does not start at the origin, so it's not proportional. Again, it still has the idea of being proportional, that as you increase one a certain amount, the other increases a certain amount, or even decreases a certain amount. So the red one was these, sorry for the wrong color, but that was the red one. So here's your 0, 0. 100 minutes is 5 bucks, 200 minutes is 10 bucks, 300 minutes is 15 bucks. Now these black vertical lines, this is not something you are traditionally going to draw. These black lines are just demonstrating the fixed costs. It demonstrates what the fixed costs does. It just shows that the fixed cost takes this line and it bumps it up $20. That's all that's showing. Because this one is $20 higher than that one. This one is $20 higher. This one is $20 higher. This one is $20 higher. That's all a fixed cost does, or fixed whatever. It doesn't have to be a cost. It just shifts things up. So again, these little black vertical arrows, this is not something you would traditionally draw in your homework, on a quiz, on a test. In Excel, you won't see them. I'm not going to ask for them. It's just a demonstration here. So don't get used to that. All right. So now that we've seen an example, let's try out one. Let's see if we can actually do this on our own. Can I zoom in? That's too far. That is just right, it looks like. All right, I'll scroll down a little bit in just a minute to that. So weight of water. The weight of water is proportional to the volume at a rate of 8 pounds per gallon. So when we say something's proportional, it just means that you can have that multiplier. You have like a y equals kx kind of setup. But then we're going to assume that we're not just going to be measuring the weight of water, we're going to have a bucket to put that water in. And we've got a really heavy bucket. This thing's made of solid steel, and it's 10 pounds. So we want to do some what if analysis. What if we put a half a gallon of water in? What if we put a 1 gallon in? How much does the water weigh, and how much does everything weigh? So this is just the water, and then this would be with the weight of the bucket as well. So we said that weight of water is proportional to the volume at a rate of 8 pounds per gallon. 8 pounds per gallon. So that means 1 gallon weighs 8 pounds. Two gallons would weigh 16 pounds, et cetera, et cetera, et cetera. Not the other way around. It's not 1 pound is 8 gallons. You have to make sure you're getting that right, which I can no longer see on my screen. So 3 gallons, 24 pounds, et cetera, et cetera, et cetera. And you could even do a y equals 8 times x kind of setup, where X is your number of gallons, and Y would be your weight. That's something that we'll get into a little more directly later, but I wanted to go ahead and give you the idea. But that's only dealing with this one. It doesn't include the 10-pound bucket, because with the 10-pound bucket, with that fixed amount that just always adds 10 no matter what, that's a fixed amount, which doesn't make it proportional anymore. It just means you take the proportional part, you take the proportional part and you just add 10. It's very self-descriptive. All right, so if you have 0 gallons of water, clearly it's 0 pounds of water. If you have a half a gallon of water, well, if 1 gallon is 8 pounds, so if you double one, you double the other. That also means if you half one, you can half the other. So half of a gallon would be half of 8 pounds, which would be 4 pounds. You could also just throw in 0.5 into this. 0.5 times 8 is 4. 1 gallon would weigh 8 pounds. 1.5 would weigh 12. And instead of keep doing math by plugging it in here or trying to think things out this way, I could just say, oh, well, every time we go up 0.5 gallons, the weight goes up 4 pounds. This is up 0.5 gallons, and this was up 4 pounds. So the next one, if we go to 2 gallons, this should be 16. If we go to 2.5, this should be 20. Every time I go up a half, I'll go to 24, 28, 32, 36. That's the pattern in a larger table. But then what we do is we want to find the total weight, because we can't just put a half a gallon of water onto a scale. You have to put it inside of something. And we found ourselves a ridiculously heavy steel bucket that weighs 10 pounds. It's exactly 10 pounds. So we just take the water weight and we add 10 pounds to it. So if there's no water, that means it's 10 pounds with the bucket. If there's 4 pounds of water in there, it's 14 pounds in the bucket included. If you have 8 pounds of water, that's 18 pounds including the bucket. 12 pounds of water would be 22 with the bucket. 16 pounds of water would be 26 with the bucket. 20 pounds of water would be 30 pounds with the bucket. Now again, the change in this red every time, it just goes up 4, up 4, up 4. But to go between the blue and the red, you're adding 10 because that's what the bucket's fixed weight was. The water is a variable weight because we're allowing ourselves to put different amounts of water in. We're not having different weights of buckets. Now I might say, well, Mr. Beckner, why don't you just put the bucket on the scale and hit tare? And I go, yes, absolutely, that's what you do in real life. But the point is, when you've got to pick this bucket up and carry it somewhere else, you're going to be holding that 10 pounds of the bucket in addition to the water. So let's go and graph these with appropriate colors. So we'll do blue for the no bucket. We're just weighing out the water. So this is what we might see on the scale if we were to hit tare. And they even plot the first ones for you kind of nicely, but that's all right. We don't have to do it. We still do, 0, 0, that's the origin. Now 0.5 gallons is 4 pounds. So we go right a half and we go up 4. These graphs are also done very nicely for you, as you will see for the blue pattern coming up. 1 gallon of water weighs 8 pounds. 1.5 gallons of water weighed 12 pounds. 2 gallons of water weighed 16 pounds. 2.5 gallons of water weighed 20 pounds. 3 gallons of water weighed 24 pounds. And this is what I mean by they're nice. All of those are on the little corners of these grids that you see, but only for the blue. It's only for the part that's proportional, not including the bucket. And then all you do is just connect and extend. I'm going to do my best to make this as straight as possible. Please do not judge me. I am on a blind tablet, nor are my artistic abilities that great to begin with. That's pretty good. Now again, me personally, I would want a graph big enough to continue this pattern and show that it goes on forever and ever and ever, or at least for quite some time. So that was no bucket. Now let's do in red with the bucket. So this is what we would have seen on the scale, but when we go to pick it up and haul it somewhere, we're really going to feel the red curve. So 0 gallons actually weighs 10 pounds because we got that bucket. Now there is no 10 directly on it, but 10's halfway between 8 and 12, and that's going to be consistent. 14 pounds with the bucket when we had a half a gallon of water. So that's going to be here about halfway between 12 and 16. Then 1 gallon of water in addition to the 10 pounds of bucket was 18 pounds. 1.5 gallons of water plus the bucket was 22 pounds. 2 gallons of water plus the bucket was 26 pounds. 2.5 ends up being, oh, I drew up 3. That's what was throwing me off. I went too far. Then 2.5 was the 30. Yes, 30. There we go. Draw. Where's my eraser? There we go. So I just shouldn't have had that point there is all. That's not a big deal. It's not wrong. I just could have done my arrow right here instead, and I'm still on the grid, which is perfect. So that's still the no bucket. Now we go back to red. I don't have the extra point plotted. It would have been off the grid. Nice straight line, doing our best. Sorry for any little perturbations. And then keep going just to show the pattern, and that's with the bucket. Now again, excluding the bucket, this is a proportional problem because it went through the origin with no bucket, but with the bucket's weight, with that fixed weight in addition, this is no longer proportional. It still has that nice relationship that every time you add a half a pound, the weight goes up 4 pounds, and that's true every time you go between points. So you could find the next one that way, 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 without having to get to the fact that this equation is y equals ax plus b, and knowing what the a and b, you're plugging it in and doing algebra and arithmetic. You can just follow a pattern. Patterns are amazing. They can get jobs done quicker most of the time. Now, they do ask for the axis labels down here. We don't want to miss that. The axis label, the horizontal one, was going up in gallons. And then this vertical one was our weight. Now, I said gallons here and weight here technically. Technically, some teachers might not like that because one is a units and one is an actual type of thing. So the gallons would be a volume, and the weight would be in pounds. So you could put gallons versus pounds, you could put volume versus weight. You could mix them up, and I would not care, but some teachers might. All right, so let's clear the screen, and let's do another. How are we on time? 15 minutes. Of course, this one is on 2 different pages, so I'm going to have to scale back quite a bit. The cost, I'm covered. The cost is proportional to the number of tickets you buy at a fair at a rate of $2 per ticket. So maybe it's 3 tickets for one ride, 1 ticket for another ride. We don't need to know all that stuff. We just know it's $2 per ticket. But in addition to that, there's a fixed cost of $15 just to get into the fair. Now you might say, that's pretty unusual. Most of the time you can just walk in and there's no fee. Well, drive to Busch Gardens and tell me that you didn't just pay 15, 20, 30 bucks for parking, which would be a fixed cost. Now, if you have 4 or 5 people in the car, you can divide out that fixed cost, but it's still a fixed cost. And then you have to pay for your tickets when you get in, which would be your variable cost based on the number of people. All right, so $2 to get a ticket for each ride, $15 just to get in. Maybe they've got shows and stuff happening to make it worth that 15 bucks. I don't know, not the point of the problem. The point is, no matter what, you're paying 15 bucks whether you ride any rides or not. If you want to ride some rides, you're paying $2 a ticket, and then, let's just say it's a ticket for every ride. Just keep it simple, not that it matters at all. So fill in the table of value. So this is just the number of tickets. Let's go back to blue. Blue, please, thank you. So this is just the cost for your tickets. This is your total cost. So if you buy 0 tickets, you're not going to pay any money for tickets. If you buy 5 tickets, they cost $2 each. So the first one costs you 2, the second one 2, 2, 2, 2. That would be $10. 2 tickets per at $5. I'm sorry, $2 per ticket, and we're getting 5 tickets. 2 times 5 is 10. So every time we go up 5 in the tickets, the cost is going up 10. So this went up 5, which means the next one will be 20. You don't even have to think about it any past that. This goes up 5, so this will be 30. That's 10 more. Then that goes up 5, so this will be 10 more, 40. This goes up 5, so this will be 10 more, 50. It's just a quicker way to do things when you've got these patterns. Knuckles popping if you hear that. Sorry if that bothers you. But the total cost, we don't just buy tickets, we have to pay that $15 gate fee, that fixed amount. We don't pay $15 for ride 1 and then $15 for ride 2. We just pay the $15 once. So even if we pay $0 for our tickets, we still pay $15 to get in the gate. If we pay $10 for tickets, we got to also pay the $15 to get in the gate. 10 plus 15 is 25. If we paid $20 for tickets plus the 15 to get in the gate, that's 35. Now look, each time this is still going up 10, so I don't have to keep thinking about it that way. I can just keep adding 10. 45, 55, 65, boom, done a lot quicker. You could also say the main idea I was going with originally was this cost in comparison to this cost. To go from here to here, you're just adding 15, and that's because of the fixed cost saying just add 15 to the variable cost. Now let's plot some points. And I meant to switch my color there. Dang it. 15, I'm going to erase it. It's going to get too ugly otherwise. Draw, so 15, 25, 35, 45, 55, 55, 65. That's a 55 there. All right, so in blue, we got the origin. 5 tickets cost us 10 bucks. 10 tickets cost us 20 bucks. 15 costs us 30. 20 would cost us 40. And then 25 would cost us 50, and that's where we stop. But I could keep going and say that 30 would cost us 60, 35, 70, 40, 80. It just keeps going forever and ever and ever and ever and ever. Because this is a simple model. Notice I just said because this is a simple model. So this was no fee, no gate fee. But then we have the 0 tickets still cost you $15 in reality to get in, maybe go see some shows and stuff. Then if you buy 5 tickets, in addition to the $15 gate fee, it was 25. Then it was 35 for 10, 45 for 15, 55 and 65 for 20 and 25 respectively. Connect, extend, and that was your total cost with your fee included. And again, I'm not doing what that original problem did. I'm not showing these little, oh, that's just demonstrating that the fixed cost adds 15 each time. That's all that's doing. Again, that is not a traditional thing that we would show, which is why I'm erasing it now. I'm just trying to give you something in relation to the first one you saw. For the axis labels, the 0, 5, 10, 15, and 20, etc., that was the number of tickets. And then this axis, the vertical one, these were costs. You could put in dollars if you like. These labels, I can't tell you how many graphs and charts I see in the media that don't have labels on them. You know why? Because they want to confuse you. They want to mislead you. Labels are critical. All right, let's do another one. Here we go. Driving distance. The distance you drive is proportional to the time driving at a constant speed of 40 miles per hour. This is true. No stoplights, no turns, no potty breaks. If you just get on the road and you're going 40 miles an hour and you're driving through the desert of Nevada trying to go count some ballots, sorry, relevant, nothing is going to prevent you from, hold on, let me say that. Nothing is going to prevent you from maintaining your speed. You can just keep going 40 miles an hour for several hours and nothing's going to stop you if you didn't drink a bunch of water or whatever. So that's what we're going with here. The distance you drive is proportional to the time driving at a constant speed of 40 miles an hour. But let's say when you were on your drive in the desert, assume that you already drove 100 miles before you started keeping track of everything. So let's say you filled up your gas at a gas station, your gas tank at a gas station. You start driving 100 miles into the desert and you realize, oh shoot, I forgot to reset my trip meter, the thing that keeps track of how many miles you've got on your tank of gas currently. You have your odometer and your tripometer. So you reset it and you go, well, shoot, I drove 100 miles. Now I'm missing that 100 miles in my trip. And if I know maybe I can go 400 miles before I run out of gas, that means when I see 300 on my trip, I know I'm going to be out of gas because of that 100 miles already there. That's kind of what we're getting into here. All right, so excluding your trip reset 100 miles already driven, if you drive for 0 hours, you will have gone 0 miles. If you drive for 1 hour, well, you drive 40 miles per hour per 1 hour, so 1 hour is 40 miles. So when our time goes up 1 hour, our distance goes up 40 miles. So when we go up another hour, we expect to go up another 40 miles and we'll be at 80 miles. Also, 2 times 40 is 80. 3 times 40 is 120, and guess what? When you go up 1, you go up 40, boom, 120. Then 160 because we'll go up another 40, and 200 because we go up another 40. Now, you knew that the 40 was going to be a multiplier, but if you do it backwards, if you took your distance and multiplied it by 40 and you thought that was time, you'd get some answers that wouldn't make sense. For example, if you think, all right, if I go 1 mile, how long is that going to take? If you took 1 times 40, that would tell you that 1 mile takes 40 hours? Wait, what? 1 mile takes 40 hours of time? No, that would not make sense. Clearly, you've done something wrong. Remember, we are asking ourselves if things make sense. We are establishing critical points. All right. So it seems like 5 hours in, we've gone 200 miles. But again, this time is just from us hitting the reset button on our trip where we had already gone 100 miles. So this is in addition to the time on the trip and the distance on the trip. So while when we hit reset on the trip, it now says 0 miles, in reality, we've gone 100 miles. We've already got that on the clock. That's the fixed amount that was already on the clock, already on the trip before we hit reset. Now when our trip reads 40, that means we've really gone 140 miles. When it reads 80, we've really gone 180 miles. When it reads 120, 3 hours into hitting reset on the trip, we've really gone 220 miles. Then 260, then 300 as you keep just adding 40 over and over and over. That addition is consistent between these two values. It's to go from one to the other. That's when we add the 100 to go from blue to red, blue to red, blue to red. That's just the fixed amount. And maybe there's another reason why we reset the trip. Maybe there's another reason we have this 100 miles factored in that we already drove. But you get the idea. So let's plot them. All right, I gotta be a little quick. 0, 0, 1 mile, 1 hour, 40 miles, 2 hours, 80 miles, 3 hours, 120, 4 hours, 160, 5, 200. This was not including the 100 miles we already drove, and we continue the pattern. So excludes the 100 miles driven initially. Then in red, what we're going to notice is we're just going to take this blue thing and we're going to lift it up exactly what that extra mileage was, that extra 100 miles. So that's a height of 100, then 140, 180, 220, 260, 300. Continue on, and that's the total distance driven. Now, as we move on through the sections, we're only going to be interested in the red one. We would not care about this blue one at all. We don't want to make 2 different graphs on the same thing. We would only do the entire model, not just part of the model. So again, in the future and in your homework, we're generally not doing just part of it. You would account for everything. Now, maybe there was no fixed 100. If that 100 was not there, then the red curve wouldn't be there at all, and your answer would just be the blue one. And again, in your homework, typically you're only doing 2 points because all you need is 2 points to form a line. I can remove all but any 2 of these points on the red one and it'll stay the same. Any of the 2 points on the blue one and it would stay the same. Right. Clear our screen, come off of annotate. What do I got, like 2 minutes left? I want to show you the next little bit, and then we'll call it a day. This is what I've been talking about quite a bit. We just didn't have it written down. Linear equation. So the equation that would make that picture that's a line can be expressed, words are hard. Linear equations can be expressed as some total amount is the variable amount plus a fixed amount. Let me put that on the same line. It's a variable amount, which was us taking the number of minutes times 5 cents per minute, then plus the fixed amount, which was us adding the $20 flat fee every month. So this variable amount is the part that changes, and in order to change, you're going to have to multiply it by a variable. I've been saying that y equals kx setup was kind of similar. In fact, it's exactly the same for that. You just take your 5 cents per minute and you multiply it by your number of minutes. But we don't know what the number of minutes is for every scenario. That's why we call it x, or m for minutes, or whatever letter you like. So when we come back next time, we're going to go back to those 3 or 4 examples, and we're going to write up equations, something like y equals 3x plus 5, where the 3x, this would be your variable amount, and the 5 would be your fixed amount. So this 3 is always the amount per blah, blah, blah. So the cost per minute, or the weight per gallon, or the driving distance per hour. So that number is always the thing that has a per in it. The fixed amount is always the number that doesn't have a per in it. It's the thing that you're just adding one single time no matter what. So that adding $20 to the cost per minute value. So this 3x plus 5 or 2x minus 7, this is going to be pretty consistent with what we see with these variable amounts and fixed amounts. So we'll finish those guided activities next class.
Like I said, we'll finish those guided activities next class, but that's a pretty good introduction to the concept of lines with the graphs, and very, 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 very brief into what the equations will look like. We'll dive more into that head first next time. But again, for now, my math lab homework's 4.2, 4.3, 4.4. You can see the dates. Midterm coming up on the 1st and the 2nd. Do not miss that. Don't forget to show your work. Names on your paper, scan your pages, submit them in Canvas within 15 minutes. And work on that review. Remember, review has questions and answers, nothing in between. You're responsible for all the in between. You do not have to do the review should you choose not to. It is not a graded assignment. It will not count for or against your grade, but I highly suggest that you do the review because it will let you know more specific what to study. Besides that, have a good day, study hard, work hard. We will see you next class. Take care, everybody.